Okay, very good. Yeah, we started kind of chapter 4. I realized we did kind of rush job. We went through 4.3 like in one lecture, 4.1, 4.2, 4.3 more or less. No, but I mean, okay, so it's a good idea to go back and cover some of the stuff that I did not discuss. So, for example, from section 4.1, so this is like level curves. And level surfaces. So this is from section 4.1, which is included in your midterm, as you notice. Okay, so what is this level curve, first of all? So given a function of two variables, like imagine you have a function of two variables, f of x and y, given, then you can ask for the set of all points where this function takes constant value, right? So let's see. P, the set of all points x and y in R2 such that f of x and y is equal to some constant, say, maybe c, little c. Okay, so for a given, maybe this is not a good idea, I call it alpha. For a given constant alpha. Okay, so you notice that two things are given, right? So first of all, this function is given, right? And this value is given. And we are looking for the set of solutions of this equation, basically, f of x, y equal to alpha. Now, this is called level curve because generically it's going to be a curve, but it could be an empty set. It could be a point, it could be a bunch of points, it could be a curve. I mean, it could be a lot of things, but generically is a curve. So this is called the level curve. Of the function f of x and y. Okay, instead of talking kind of abstractly about the notion, or the notion is defined abstractly like that, but let me give you an example so that you can see what's going on, and then you can just we can just discuss it from there. So here's an example. So let f of x and y be equal to, say, I just take the simplest thing, x2 plus y2, for example. x2 plus y2. Right. Okay, now let's draw the level curves of this. So find level curves x2 plus y2 equal to 1, 0, minus 1. So this is your f of x and y now, right? This is your alpha, or 0, or minus 1. So this is like three problems packed in one problem, right? I'm just asking to find a level curve for values alpha equal to 1, minus 1, 0. So we have to solve three problems to gain some insight into this issue of level curves. It's a very, very important concept, as you will notice. So let me draw this part, and then we can just. Okay, So first of all, we want to find, so alpha equal to 1. So C is the set of all x and y such that x2 plus y2 equal to 1. You can draw this curve. You have done this in high school. X2 plus y2 equal to 1. It's a circle. Right? It's just a circle. So you just draw a circle. That's it. So that's the level curve for function x2 plus y2 for value alpha equal to 1. So on these points, this function takes the value alpha equal to 1. Okay. So we say that the level curve is a circle. Let's see if there is a question in the chat. No. And let's take alpha equal to now 0. So in this case, C is equal to the set of all x and y such that x2 plus y2 equal to 0. So what is the level curve in this case?
Just the origin?
Just the origin, exactly. Just the origin. Just we call it level curve, but it's not a curve. It's a point. But yeah, you'll see why. So this is equal to 0, 0. Just 1 point. Just origin. Okay. Now let's look at another point which we are asked. We are asked also to treat the case alpha equal to -1, right? To find the level curve for alpha equal to -1. So this is the third case. Let's do that. Okay. So in this case, we want to solve this equation: x2 plus y2 equal to -1. So what are the solutions? What is the level curve in this case?
The empty set?
It's empty set. There are no solutions in other words, right? There are no solutions to this. So C is equal to empty set. Empty set. Okay, so we have found level curves, so-called level curves, but we notice that only for positive values, this is really a curve, which is a circle. For one value, it's a point, and then for lots of values below 0, there's nothing. But that's fine. So it's always a good idea to draw all these level curves in one plot, and then you get an idea of how this function kind of behaves. So I'll explain more, but let me just tell you. So these are like all these concentric circles. So for example, this is alpha equal to 10, here is alpha equal to 9, and so on. Here is alpha equal to 0, and there is nothing else. So by doing these level curves, by drawing them all in one plot, one coordinate system, you are indicating something, right? We are indicating that the function takes value 10 along all these points. It's constant along all these points. And then drops to 9 as you move towards the origin. And it takes smaller and smaller values. Then you go to the origin, which takes the value 0. So you just take that value. So have you seen such maps, such drawings?
Like when we take a limit and we approach it from any direction, so it's kind of like a circle tilting on a point.
Yeah, limit certainly is there, but in kind of, have you gone hiking or got maps of regions? Yeah, topographical maps, exactly. These are exactly the same things. That's what you get in those maps is that it shows that if you walk along this path, you are at altitude, for example, 10, and here you're at altitude 9, and so on. Of course, this is a very simple case. In reality, nature, the kind of features, natural features, is much more complicated. Land, goes up and down. You really see some little more complicated than that. So, but this is essentially these topographical maps, indeed. So that's so level curve are very, very useful in giving us the idea of this function. So now, this is the function f of x and y equal to x2 plus y. Now, we can do something else with this function. Instead of drawing the level curves, we can draw the graph of the function, right? So that's the kind of going into 3 dimensions now, right? So instead, I mean, yeah, okay, instead of drawing level curves, which is a very good idea, can draw the graph. Graph of f of x and y equal to x2 plus y2. So this graph is going to be a surface in 3-dimensional space, right? So, and then you get a surface in 3D. So that's interesting. You have one function, f of x and y equal to x2 plus y2. You can do 2 things with it. You can either draw the level curves, which gives you these curves in 2D, or you can draw the graph, which gives you a surface in 3D. So it's just going down or going up. You can do both. You can play both games, and they're quite related. So let me draw the graph. So what is the graph of this function? So graph is the set of all points x, y, f of x and y. So just the third coordinate is not arbitrary. It's going to be determined by the first 2 coordinates, which is x and y, right? So that's what it is. And then, so we can draw it like that. So in this case, it's going to be the set of all x, y, x2 plus y2. So this is a 3-dimensional thing now. Right? So we can draw this graph. Z equal to, so this is like Z, the third coordinate, right? So this is Z equal to x2 plus y2. Okay, so this is your graph, and if you want to draw the coordinate axis, this is x, this is y, this is z, and that's of course we have seen such surfaces in chapter 3, right? These are what these surfaces are called, by the way? What was the name of this sort of surfaces? Quadratic surfaces, that was the general name, that's absolutely correct. And then for this particular one, it's called, what's that?
An elliptic paraboloid.
That's an elliptic paraboloid, absolutely correct. Actually, we can say, in fact, in this case, it's a circular paraboloid because it's really the circle, but yeah, it's an elliptic paraboloid. So this is a paraboloid, indeed, elliptic paraboloid. So, okay, so we have these 2 things. Level curves are here. Graph is here. And you see the relation between the two, right? Imagine this is some sort of geographic feature, some kind of land. There is a bottom of a valley or some bottom of some maybe there's a quarry somewhere, something like that. It's just, kind of land has been removed from here, for example. And then, so if you have such a thing, you can actually give the idea of this feature of the land either by drawing this, which is possible but a bit difficult, or you can just give this to your readers. So that this is the feature of the land, and usually people put here things like 0, 1, 2, 3, 4. It means that if you're walking along this line, you're walking along the height 2, for example, which means you're really walking here, right? 0, altitude, 1, 2. So yes, we did the graphs in previous previous section, and now we are doing level surfaces, like level curves. Sorry. So let me give you another example. Any question about this? No? Okay, there's no question there in this chat. Okay, so now let me give you some something which is maybe a bit more kind of interesting. So here is another example. Draw level curves of x and y equal to x2 minus y2. F of x and y equal to x2 minus y2. So we have to draw x2 minus y2 equal to some constant. And then we choose that constant. We have to be very general, so we choose positive, 0, or negative. And then we'll see how this changes. So first of all, the easiest case, with curves, you see I'm saying x2 minus y2 equal to 0. So what are the level curves in this case? Well, x2 minus y2 equal to 0 means that x is equal to y or x equal to minus y, right? So there are two possibilities. So it gives me x equal to plus minus y. So this is now, okay. So this is obviously x equal to y, x equal to minus 1. And there are two solutions, but this is okay. But still we call it level curve, although this is really two curves, two straight lines coming together at the origin. Okay, now x2 minus y2 equal to 1. So what is that curve? x2 minus y2 equal to 1. Remember from maybe linear algebra or from geometry. Anyone can name that curve x2 minus y2, or can you draw the picture of that curve x2 minus y2 equal to 1? Yes, that's correct. Yes. It's a hyperbola, right? This is a hyperbola. Is a hyperbola, right? And if you want to draw this, you notice that if y is equal to 0, x is plus minus 1. So it means that it's passing through this. Plus 1, minus 1. So okay, so that's it. So you can draw like an x2 minus y2 equal to 2, 3, etc. And then you get different hyperbolas like this. right? So as you move to the right, you're picking bigger and bigger values, right? As you move to the right. All right, so that's one of the hyperbolas. Now, the other one, if x2 minus y2 is equal to -1, let's look at that, right? x2 minus y2 is equal to -1. What is that curve? That curve is also a hyperbola, but in this case, if you put y equal to, you cannot put y equal to 0, because if you put y equal to 0, you get x2 equal to -1, which there are no solutions. But you can put x equal to 0, so it means that if you want to know what's the x intersection here, you put x equal to 0, you get y equal to ±1. Put y equal to +1. So this is the point, and then this is another branch of hyperbola. I mean, another kind of hyperbola. It's similar. Okay, so this is -1, and you can, this is +1, and then as you move on, you get bigger and bigger, or smaller and smaller, rather, negative numbers. Right? So, okay, so on this one, on this part, this function is taking negative values. That's why you're getting all those curves passing through this part, and also this one. And then on the right-hand side, the function takes positive values. x2 minus y2, for example, is equal to 1. Here, the mirror image also takes positive values because, I mean, it doesn't matter for this one. So we have, exactly, so that's the profile of this function x2 minus y2 equal to -1. This is the function. Okay, so this is the level curves, right? So these are the level curves in this case. But again, we can also look at a graph of the function, because graph of x2 minus y2. So this is like z equal to x2 minus y2 is a surface, right? Z equal to x2 minus y2 is a surface. Can you name this surface?
Is it a saddle?
It's a saddle, yeah, that's exactly. And the other name?
Hyperbolic paraboloid?
Hyperbolic paraboloid, exactly. So hyperbolic paraboloid. Why is it paraboloid? It's because it's degree 1 in z, right? Z equal to y2 or y equal to x2. 1 degree 1, 1 degree 2 is paraboloid. It's this one. It's because of that. Why is it hyperbolic? It's because of this difference of two positive points. And that's the feature that gives you these nice drawings like that.
So if z was squared, would it be a hyperbolic hyperboloid?
So this one?
Yeah. What would make it a hyperbolic hyperboloid?
Hyperbolic?
Hyperboloid. Is that even?
Oh, no, don't ask me this question. No, I'm not sure. Let me draw this. That's easier for me. Can you draw this? Can anyone identify this surface? So that's square equal to x2 minus y. That's an excellent question that was asked, by the way. Okay, so let me read the chat. Hyperboloid. Yeah, you're answering previous question. Yeah, no, that's good. But what about this one now? What is this surface? It's part of the theory of quadric surfaces, right? That's what we did on quadric surfaces. Can you identify the surface?
Elliptic cone?
Elliptic cone. Yeah, it's a cone. Exactly. It's a cone. How do you see that it's a cone? Well, you have to bring this to the left-hand side, right? So if you bring it to the, so let me just say this is a cone. In fact, it's really honest cone. So bring it to the left-hand side, you get z squared plus y squared equal to x squared. Okay? So yes, this is a cone, but it's not the usual cone z squared equal to x squared plus y squared, right? What is the axis of this cone? Well, a cone has an axis, right? Well, what axis is the axis of this cone? Yes? It's the x-axis, right? This cone is along, is kind of, it's kind of sitting along the, or located along the x-axis. So let me draw the cone and then put the axis. That's the trick, right? So this is the x-axis and y-axis, z-axis. So the cone is certainly is along the x-axis. So as x moves, you get Usually when I drew the cone, it was like z squared equal to x squared plus y squared, right? So that was like that. But that's the cone, which is like z x y. That was that cone, but that's this cone. So it's important to realize that you can switch the role of x, y, z, because x, y, z don't have intrinsic geometric meaning. They are just labels for coordinates, and we can just choose any one. So this is kind of gives you an idea of level curves and graphs of these functions of two variables. Now we can go to one variable up. So we look at, instead of function of two variables, we look at function of three variables. In that case, we'll have level surfaces. Okay, so any questions? Oh yeah, that was correct. Yes, I appreciate that. Yeah, very good. That's a correct answer. Yes. Okay, now let's look at level surfaces and see how they arise. Level surface. So to have a level surface, we need a function of three variables, right? So it's given. And then S is equal to the set of all x, y, z, such that f of x, y, z, again, take some constant value alpha. This is called, this set is called the level surface of function f corresponding to value alpha. This is a level surface of f for value alpha. Okay, so again, instead of talking in general terms, let me just give you an example and then you understand what's going on. So here's an example. Okay, again, I start with very simple case. For example, find level surfaces of x of, so put it like this, f of x, y, z equal to x plus y plus z. So that's a very simple case because the function is actually a linear function of three variables, right? This is the simplest case, more or less. I mean, you can have like constant 1 or 2, so that would be of degree 0, but that would be very trivial. So we want to draw the level surfaces of this. So can you tell me what are the level surfaces of this? Of this function?
Yes, they're planes.
Your planes, exactly. Planes of with the equation x plus y plus z equal to alpha. So S is equal to the set of all x, y, z, such that x plus y plus z is equal to alpha. So we can draw. I mean, this is like one of your assignments, assignment 1 kind of question. So we can draw these planes. X, Y, Z. Okay, so here is one. Okay, so I just draw the portion of the plane that is in the first kind of, I wouldn't say quadrant, first octant, right? Okay, so then you can have and then here there is a plane that passes through 0, x plus y plus z equal to 0. So I don't draw that plane. There is a plane that passes through 0. And then you go in the other direction, you pick up negative values. So it's really a family of planes parallel to each other. And it's just like, so I just say it's a family of parallel planes. So that's it. Now here is, let me give you another example. Any question about this? So there was a question. All of R3. So the question is it all of R3? I'm not sure what you mean exactly, all of R3. Yeah, it goes through, yeah, I mean, perhaps you mean, I said I just draw the portion that is in the first octant. But you can imagine this is everywhere, if that's what you mean. All right, now let me give you another example. So find level surfaces of function f of x, y, z equal to x2 plus y2 minus z2 plus 2x plus y plus z. So say f of x, y, z equal to 1, 0, and minus. So I want you to do the level surfaces, draw the level surface of this thing for 1, 0, and minus 1. So let's start with 1, right? So the question is, how do you draw this surface, x2 plus y2 minus z2 plus 2x plus y plus z equal to 1. It looks like it's something that we have been there before, right? We have been here before. Yes.
You complete the square.
We complete the square, it's a quadratic surface, and we rely on our memory, and then hopefully your memory will be better than mine, and then you know. But you have to be better. You have no choice, right? Because you have to write the exam. I don't. Okay, so this is equal to 1. Okay, so now we have got this, what is it? Complete the square as it was suggested. So we've got x plus 1 squared. And then this is minus 1. And then we have plus y plus half squared. So this, that, the tackle, this and that is going to be minus quarter. And then there is minus. So how do we deal with this z2 minus z? Well, this is z minus half squared. So minus z minus half squared. And then we have what? We have here, so it should be minus quarter equal to 1. So make sure you understand this very first step. Right? You understand this first step, what we did, okay? And make sure we didn't make any mistakes. So, but then now we can move on. So this is x plus 1 squared plus y plus half squared minus z minus half squared. And now, what are these values? Negative 1, negative 5 over 4 goes, oh, this actually luckily cancels with this. Yes, and then this is equal to 2. So this is the equation. This is the equation. Very good. So we are back to chapter 3 again. And so this is a quadratic surface. But we have to know which quadratic surface is that. So we have to know what's this. What quadratic? Yeah.
A hyperboloid of 1 sheet.
Is it hyperboloid? It's hyperboloid of 1 sheet. Okay. I have to think. Right. So what was the hyperboloid of 1 sheet? How did it look like?
Like a series of ellipses that kind of grew.
Yeah. So this was like your. This is the one. Right? So it's like a nuclear power plant. If you go to Bruce up here, you have one of these, maybe several. Okay, so we have that. Okay, also near Toronto, near Oshawa. Okay, anyhow, so we have this. So in this case, if this is Z and X and Y, so what's the equation for this? This was, remember the equation for this. What was it?
What was the general equation?
Yeah, general equation. I mean,
X squared over a squared plus y squared over b squared minus z squared over c squared equals 1.
minus z squared over c squared equal to 1. So what was our reasoning? We brought this to the right-hand side, and we said that, okay, even if z is equal to 0, so you're like at this level, then you're going to get ellipse x squared over s squared plus y squared over b squared equal to 1. So this would be this ellipse. And then if z grows, as z grows,
I think you wanted Z instead of a B under Y squared.
what was that?
Under
Oh, yeah, this is, yeah, absolutely. Thank you. Yeah. Yes, thanks. Very good. Excellent. So now we have that. So we have these ellipses. Yeah, indeed, as it was said, it's a family of ellipses like that. It grows. And okay, so this is it. And in this case, actually, it's exactly all right. It's just like right on the nose is just like that, except for what? This is exactly of this type, except that the coordinates have been shifted, right? Okay, so in this case, so this is, so yeah, so what was it? Hyperboloid of one sheet?
And also, wouldn't they be perfect circles in this case and not ellipses?
In this case?
Yes.
Yes,
All the
yes,
denominators are
exactly. Yeah, exactly. Absolutely. Because A and B are equal to each other if you have lambdas. Exactly. So this is a hyperboloid of one sheet. Passing through point. Okay, so this point, I mean, passing through is not correct. I mean, center that, I would say. Center, I mean, it's also not very correct, but I just write it. Center at, well, x equal to -1, y equal to -½ and z equal to. So -1, -½ half. So it just means that this point is not really the origin. This is the point now, -1, -½ Excellent. Thank you so much for all your help. Okay, now, so this is hyperboloid of one sheet. Can you give me an equation for hyperboloid of two sheets? Yes.
X squared over A squared minus Y squared B squared minus X squared B squared equals 1.
Exactly, yeah, exactly. So if for some reason, for example, you had here negative, this would be two-sheeted. In that case, it would be so, but that's not the case yet. Okay, but we just did it for the value equal to 1, and then you can do similar analysis for 0 and -1. It works. That's not a problem. Okay, but can you draw the graph of this though? Can you draw the graph of this function? Yeah.
Like, would we just draw the hyperboloid one sheet with the proper center?
No, you see, yeah, I know what you mean, but look at it like this. What would be the graph? The graph would be something in 4-dimensional space, right? Because there is 3-dimensional domain of the function, which would be x, y, z values. And for each x, y, z, you have to find a w in 4-dimensional space. But we cannot imagine 4-dimensional space, so that's not very feasible. I mean, this exists as an object in 4-dimensional space. Is a surface indeed is a 3-dimensional object in this 4-dimensional space, but it's very hard to imagine. So we don't draw it, at least not in this course. Well, people have some ways of drawing 4-dimensional objects by projecting into 3-dimensional objects, as the way we did like for 3D, projecting to different 2Ds and trying to come up with some devices to kind of aid our imagination, but it's very difficult. Any questions? Yes?
How would we draw the level surface of this?
Oh, that's what we did. This is the level surface.
But do we like sketch it? Do we have to know how to sketch?
Oh, you mean many of these? Oh, yeah. That's an excellent question. Yes. What happens is that no, that's excellent. So let me then okay. So let me now tackle the case where we don't have to analyze like that. I just write x2 plus y2 minus z2 equal to something, and then I draw it. Yeah. Let's do those. Exactly. So then here's an example. Level surfaces of so x2 plus y2 minus z2. You know, that's what you're asking essentially, because essentially it's just that, just the right hand side, the value on the right hand side changes, right? Okay, now if this is equal to say x2 plus y2 minus z2 is equal to 1, 2, 3, etc., is a positive number, right? It's bigger than 0. We know what these surfaces are, right? What are these surfaces? These are families exactly of these nuclear power plants, one built kind of stacked on over each other, right? So let me try. And then you have this one. And then there is one inside. And there is one inside. So on and so forth. So it's a kind of, it's just, yeah, I mean, it's a sequence of these hyperboloids of one sheet, kind of layered on top of each other, like stacked on top of each other, like that. So it goes. Okay, but then at one point you have to deal with the case where this is equal to 0. So there is a phase transition at that point. At that point, something changes, right? You're not dealing with a hyperboloid of one sheet anymore. You're having a what? A cone, yes. So somehow there is also a cone inside this. Yes. Of course, not to the scale that I have drawn this thing. So there is this cone. Okay, so those hyperboloids that correspond to bigger values, they are outside. Right, so like still, they're like that. Right? So these are the ones that correspond to positive. So here is a positive value, here is 0, and you can imagine if you move inside, you're going to get hyperboloid of 2 sheets. Let's see how it works. So for example, so the case that's remaining is negative, y2 minus z2 is equal to -1. Why is this a hyperboloid of 2 sheets?
You can multiply by -1. And then
You can multiply by -1 and then reduces to that case, exactly. So if you multiply by -1, you get z squared minus x squared minus y squared equal to 1. And this is indeed a hyperboloid of 2 sheets, and it's all inside the box, right? So these are inside. So this is actually extremely interesting set of patterns, right? So you have all of them in one picture. So you have these hyperboloids of one sheet, they come together, they then degenerate into a cone, and then they start kind of turn. So yeah, this is very interesting actually. At this point, it's just everything changes. There's a phase transition, and then you get into this hyperboloid of 2 sheets. So this was a very good question. Excellent. So I think we covered ground, everything. So we are done. So if you have any questions, maybe. Okay, it looks like there are no questions. Well, let me just pause.